All right, good morning. Good. So today we're going to be looking at a new chapter, chapter 15. We'll look at sections 1 and section 2 simultaneously. And we're going to be switching gears now, be looking at integration, double integrals over rectangles. Okay, so let's again take advantage of what you already know about single variable calculus and then expand our knowledge to cover multivariable. You remember that if you have a function of one variable, y is equal to f of x. And let's say it looks something like this. Suppose we wanted to find the area under this curve from A to B. You remember this problem? You might remember that we started by using what's called the Riemann sum. And all we did was dividing this region into a bunch of rectangles. And here I'm going to use 3 rectangles just for illustration purposes. And then using Riemann sum, we estimate the area underneath. So area is roughly equal to sum of the rectangles. Right? And you remember that we had choices of our sample points. We could, for example, use the left end points of each subinterval as our sample point. Or we could have used the right end point I'm just duplicating the same picture here. Maybe I shouldn't have used so many colors, but it is what it is. And here we could use, for example, the right end point of each one. That's the representative point. So that's the left, right. And we also have the choice of using the midpoint, if you remember the midpoint rule. Right? Remember that? Yes? Okay, so we found out that the area is roughly equal to the sum, n is however many rectangles you wanted to use, and xi, of course, this is where our sample point is. Left, right, or mid. And then we took the limit, shrinking delta x to very, very tiny, small number, while at the same time increasing n to a large number. Exact area if n goes to infinity, right? So we learned that if we take the limit of that expression above, we get a definite integral from a to b f of x dx. Right? Nothing new here, just a very quick review of the concepts we use, because we're going to be following pretty much the same logical progression. Now we move to a function of two variables. The geometry, of course, changed. Now the function in two variables will be a surface. And we'll be talking about the volume under a surface and not just the area under a curve. Z is equal to f of x comma y. Okay? And now we want the volume of the solid under that surface. Over some region. And for today, we're just going to consider the volume of that solid under this surface over a rectangle. We're going to make it very, very simple. Eventually, we'll look at what happens when we're over some general region, maybe an ellipse, maybe a circle, maybe something that's just very, very general. But for now, we're going to make it very, very simple. So a problem statement is going to look something like volume under Z is equal to f of xy over x is between A and B, and y is between C and D. And this is very often also written this way. We often call that region R. And you see this notation a lot. The first set of brackets tell you that the interval for x. So x goes from A to B. And then there is a multiplication. That stands for, we're looking at a rectangle now. And y ranges from C to D. Okay? So get used to both of these notations. And what might this look like? Now, this is going to be a little bit harder to sketch because we're dealing with 3 dimensions, but we'll give it a shot. So imagine I got this surface here. And I want to consider the solid that's formed by all the space right below it above some rectangle. Let's just do the rectangle here. This is A, B, C, and D. So we get this kind of a column kind of shape, starting from the base, and it grows all the way until it touches, fills up the space under that surface completely. Right? Can you visualize that? This stuff we're dealing with? It's kind of like a candle in a way, right? Starting from, but it's going to be a square kind of candle thing. And how do we find the volume? We're going to use Riemann sum again, using exactly the same concept we just saw. And first of all, we're going to subdivide this rectangle into little chunks. And here I'm going to divide into just 4 little sections. Now, from each one of these little ones, I'm going to form a rectangular bar. All right, here's where artistic ability, which I lack, comes into play. So use your excellent imagination to see what I'm trying to do. How's that? You get it? What this is doing? It's a flat rectangular bar. I better not do any more, it'll get worse. So right, that's one of these bars. So what I'm going to do is calculate a volume So what do? We find the volume of that. And volume is very simple, right? It's the base is a square or rectangle multiplied by how high it is. Missing one last edge here. Right, so that's a bar. That's a rectangular bar. Okay. Now, just like with the one variable Riemann sum, we have to make a choice of how we get the height of the bar in the one variable Riemann sum and the column in the two variable case. So we have to make a choice, left, right, midpoint, and we have more choices here in 2 variables. So if you look at the region here, for each one of these small squares, how many sample points do I have? I could potentially choose. What do you think? Think about the Riemann sum, left, right, mid. How about here? For each one of these squares, let's take this one right here. How many different sample points could I have used? 5, right? I could have used the lower left, lower right, upper left, upper right, or mid. I have 5 sample points I could choose, simple ones. Lower left, lower right, upper left, upper right, and of course, mid. And I'll just sketch a couple of these. So here's our lower left. I calculate what the function is at that point, and then I use that to represent the height of that bar, of that column right here. An upper right one will be over here, of course. So I calculate a function at that point, use that to represent a column that comes out of here. So in this view here, imagine we have some kind of surface over here, and I'm trying to find the volume of that candle underneath that surface. Okay, you get the idea? All right, let's do an example to make this more concrete. One thing to know, when we extend that thing to 3 variable case, we can no longer sketch pictures like that because we're dealing with 4-dimensional things with 3-dimensional projections. We can't think about that. But mathematically, we could do exactly the same thing, just like vectors. In 5 dimensions, we can't visualize a vector anymore, but we could operate with a 5-dimensional vector mathematically. All right, so here's an example. Let's estimate the volume under z is equal to f of xy equal to x squared plus y squared over this rectangle. Remember, in this notation, we're listing x first. X goes from 0 to 2, and y goes from -1 to 1. All right, so now we're going to make a choice. How many subintervals in each direction? So here's a choice you have to make. I'm going to just make it simple. Use 2 subintervals each. I'll use 2 in x direction and 2 in the y direction. Now in the book, I believe they use the letter m for the x number. Let me look it up for you. Yeah, they use m. So in the book, they use m for that, and we use n to denote the number of subintervals in the y direction. Here I'm going to make it simple, just 2 and 2. And then you have another choice. What sample point to use? And here you make a decision, you stick with it for all the little sub-rectangles. Yep. And again, I'll make it simple here. I'm going to use the upper right. That's a choice. I'll spell out right here. Upper right. All right, so those are choices that you have to make before you do a Riemann sum. Just like with the one variable case, you make your choice how many rectangles to use and what sample point to use. Exactly the same process right here. Okay, now in this view here, we're looking down. Our surface is over this region right here. We're looking down onto the rectangle we're dealing with. And here we're talking about 0 to 2 for x, 1, 2, and -1 to 1 for y. And here we have it's a square, but in general, it's a rectangle. Okay, so once again, imagine some kind of surface floating right above it. And then we extend it down, and we have this kind of solid candle shape that we want to find the area of. We made a choice to divide x and y both into 2 subintervals. So here we go. Here are the 2 subdivisions. That gives us 4 columns to deal with. I'll just label them for clarity here. We have 1, 2, 3, and 4 columns to worry about. And the upper right of each subinterval is where we take our height. So the first one is right here. That point, the value of z at this point will represent the height of column 1. Make sense? Okay? And then the value of z at this point will represent the height of column 2. and that's for 3, and that's for 4. So there are my 4 sample points. Okay, let's calculate the volume. First one here, the height, is f at 1, 0, right? X is 1, y is 0. Everybody see why I use 1, 0 here? Yeah? It's the upper right point, which is 1, right? So the volume is, how wide is this thing? Let's call that delta x. That's 1, yeah? And that's delta y. That's also 1. In general, they won't be 1, of course, but again, I'm making things very simple here just to get the idea across. This could be a 2, this could be a 3, but you deal with them exactly the same way. The volume of this column right here would be the base area times the height. So this would be 1 times 1, right? This is delta x, delta y times 1, and this is my height. So for column 1, the volume is 1. 1, whatever unit that we were dealing with. All right, what about 2? Someone calculate 2 for me. First of all, what's the height? Four, right? Height. Because the sample point is at 2, 0. And that's a 4. And all the base areas are the same. So it's 1 times 1 times 4. Volume is equal to 1, 1, 4 equal to 4. All right, we get the idea? Yeah? I've got 2 more here. What's the volume of 3? 2, yeah. Everybody see 2? Yes? Same idea, right? How about 4? 5, good. All right, so now we got the 4 volumes of the 4 little columns. And therefore, the total volume, of course, this is an estimate because we're using these flat rectangular columns. That surface will in general be curved. We can't get the exact answer doing this. It may come pretty close, but in general, it won't be exact. And this will be, of course, 1, the first bar, the second bar, the third, and the fourth. So that's equal to 12. All right, does that make sense? Let me see heads nodding and heads shaking. Make sense? Good. Now, just like the one variable case, to improve, we're going to have to shrink delta x and delta y. And that, of course, results in increasing number of subintervals. Exactly the same concept we got earlier. When we do this, what we actually did, it might have been hard to see, but we actually did a double summation because we summed up all the rows first and then the next one up. Right, look at the order we did. First we summed all the way across, and then we did 3 and 4. And if there were more above them, we would keep going this way. Right? So what we did behind all of that simple calculation we did was a double sum. So I'll just write this down because we won't be dealing too much with this summation. So the outer summation, this is sum over x. While we hold y constant. And the second summation is sum over y, while we hold x constant. And this right here, that's just our sample point. Xij, Yij. I is how we count x, j is how we count y. Here we use 2 for each one. M and n were both 2, but in general, they could be anything. And delta A, this is the base area of each column. Sorry, this is estimate here, so roughly equal to. And now just like with the one variable case, we're going to take a limit allowing both m and n to go to infinity. So exact area. Why did I use A? This is a volume. Volume. Exact volume. V is equal to the limit with m and n both going to infinity of our double sum and in the one variable case, once we apply the limit to the summation, that summation turns into an integration. Exactly the same thing here. This will turn into a double integration. So 2 integration symbols, and underneath this R, this is the region. This is the region the surface is over. It's the rectangular grid that we worked with in the earlier, in the example we just finished. That's the rectangular grid. That's what this R here is. And then in here, we integrate f of xy and some differential element of area, dA. All right, so this is called a double integral for obvious reasons. Sometimes called the iterated integral. And it's called iterated because of this double sum here. We sum over one thing while holding something else constant. And then we sum over some other thing while holding the other thing constant. We iterate a process one variable at a time. Okay, so let's calculate the exact volume of the one we just estimated. And then we'll compare to see how good the estimation was. All right? So exactly the same thing we just dealt with. The same function, the same rectangular grid. To calculate this volume, it's a double integral over this grid. And this grid, remember, runs from -1 to 1 for y and 0 to 2 for x. So there's our grid. When we do double integral, each integral gets an interval. And there are two ways to handle this one. We're integrating the height of that surface. That part is simple. And now here you have to choose. Do you want the outer integration to be referring to x or referring to y? You can use either one. So let's write down the x one first. So the outer integration refers to x in this particular way we're doing it. And then the inner one is y. And you have to be really careful when you line up your dy and dx. So dy is going to happen first, right? Because the integration runs over y. And then dx, because the outer integration runs over x. But because this is a rectangle, we can sum these things any way we want. We could have summed them across first and then move up, or sum them bottom to up and then move across, right? So we could have switched these over. We could also have done this. You guys just got to be really careful that your dy and dx line up inside out. So 0 to 2, this is referring to x. This will be a dx going with that, and then a dy referring to the interval of y. So that's a very important thing here. If R, the region we're summing over, is a rectangle, order does not matter. This is not true in general if R is not a rectangle or square. If R is a circle, for example, then we can't arbitrarily interchange the order of integration. Okay, so let me carry out the process for you on one of these, and you get the idea. This is a very, very simple idea. Very simple process. Let's take the top one here. The outer is 0 to 2. The inner one is -1 to 1. We're integrating x squared, y squared. And then first we run over y from -1 to 1. And then we do the x, because x goes from 0 to 2. And the way you handle this thing here, you integrate these things one at a time, inside out, from the innermost integration first. So first we look at this one, the inner one. that dy tells us that the variable is y, and x is treated like a constant during the inner integration. It's the exact opposite of partial derivative, right? Remember, in partial derivative, we hold one thing constant, treating the other thing as a variable. Exact opposite of that. So just like partial derivative. Does that make sense? All right, so let's do that. We're not touching the outer integration yet. Let's just evaluate what's inside here. X squared is a constant, so this is like 2. If you integrate 2 dy, you get 2y, right? So here you're going to get constant times y. And then integrating y squared, we get y cubed over 3. And this is evaluated from y is minus 1 to y is equal to 1. So that green box becomes this green box right here. Does that make sense? Yes? Okay, we keep going. 0, 2. Now we're plugging 1 for y. The usual way you integrate is exactly the way you've done before. So we get x squared plus 1 over 3 minus negative x squared minus 1 over 3. Okay, everybody see what I did here? Yeah? Keep going. 0 to 2. Simplifying this, we get 2x squared plus 2 over 3. Okay, so that completes the inside integration, the green box, right? We're done with the green box. Now we're going to the outside now. And now this is just a very, very standard, typical integration we have done a gazillion times. We can all do this in our sleep, I hope, and watch me screw it up. No, I'm not going to screw this up. 8 plus 4 over 3. So, oh my God, what did I do? No, 2. Wait, what did I do wrong? 2 over 3 here, yeah? Oh my God, what did I do? So this eventually, if we do this right, which we should, 20 over 3, yeah? All right. So that's the exact volume. Exact. Earlier, our little rectangular estimation, we got 12. You know, we didn't expect that to be exact, but at least it's not too horribly bad. You would get exactly the same number if we had done x first and then y last. But the idea is exactly the same. Questions about this? All right, let's do another one. All right, so here we got double integration. So, interpret this in terms of a solid. Yeah, this is a volume of solid under the surface ln of x over xy squared, which we can't visualize really. I don't even know what that looks like, but whatever, it's what it is, over the grid. X is running from 1 to 5, and y runs from 1 to 3. Notice the ln of x here restricted us to positive x, which we are running in positive direction, and also the xy squared downstairs restrict us to move away from both axes. So we have to be trapped in the first, where x and y are both strictly positive. But that's okay, because our intervals are perfectly fine. Okay, we handle this exactly the same way. We integrate inside out. First, we consider the first integration with x, treating y as a constant. And here's one thing you could do, because in the innermost integration here, y is treated as a constant. So we know we can always pull a constant out of an integration, right? Or we can put a constant in, however we want. So you could move that y squared out of the way, just to get it out of the way. And just worry about the ln of x over x. Because first integration is x. So y is a constant, which we're free to move in and out of an integration however we want. So we're down to worrying about this one here. And so once we're done with that, it'll be a something. We lump it with the y squared and then deal with it. Yep. Okay, how do we integrate this? I didn't understand that response, but let me ask again. How do we integrate this? What's that? Yes, how did you get that? You did something in your head. I'm looking for that process. Substitution, yeah? Substitution, right. With u equal to ln of x. And you did that in your head because all of you are geniuses, right? You can all do this. We've done this before. I'm just trying to bring back your memory in case you're a little bit rusty. So that means du is 1 over x dx. Also be careful. Don't forget to deal with your integration limits when you do a substitution. The old integration limit of x is equal to 5 now becomes u is ln of 5. And the old integration of 1, x is equal to 1, becomes u is equal to ln of 1, which is 0, right? So the integration becomes 1 over 3, 1 over y squared. That thing is just waiting. That thing has to wait. Y has to wait until x is done. It has to take its turn, yeah? It's like playing baseball. You got to wait for the one team to bat first, and then your turn to bat. Same thing here. So this guy here becomes 0 to ln of 5 u du, right? I don't know what that's doing. Whatever, try to ignore that. Okay. now we integrate that. 1 over 3, 1 over y squared, and that's u squared over 2, with u being 0 and u is equal to ln of 5 as the limits. When you do an iterated integral, write out exactly what what you are substituting in. So u equal to 0. Because often you're going to have two variables mixed up in here. If you don't write down u is equal to ln of 5, you just write ln of 5. There's a risk that you forget what you're substituting in. Just write it out explicitly until you get comfortable with this process. So this will be 1 over 2 ln of 5 squared. Which is just a constant anyway, right? This thing is a constant. So we're integrating constant over over y squared. And that's a trivial thing to integrate. I should not have said that because then I will screw it up again. That is a very hard integration. So 1 over 3, 1 and 3, right? So this is 1 over 2 ln of 5 squared times y to the negative 2. We'll just use power rule to do that. That whole thing is a big lump of constant. Take it out. And this is negative 1 over y, 1 and 3. Okay, notice I didn't write y is equal to 3 and y is equal to 1 because I only got one variable left. I have no other choice. But in the earlier round, the good practice is to have written explicitly x is equal to blah or u is equal to blah if you had to use substitution. Okay, finishing this up, we get negative 1 over 3 plus 1, which is then 2 over 3 times that. So, okay, ln of 5 squared over 3. Okay? Again, remember, because this is over a rectangle or square, we could have swapped the integration. So let me finish writing this. Same answer if we did 1, 5, 1, 3, ln of x, xy squared, dy, dx. Because we could swap the integration, order of integration, dealing with over rectangle, any order we want. So sometimes you need to look at the stuff you're integrating, and perhaps a swap will make the first round of integration easier to carry out. But then you have to pay the price later with the outer integration. It's a choice you have to make. Look at the stuff you're integrating, decide for yourself. Okay, that's it for today. See you Friday.